We're going to talk about conservation of energy. The law of conservation of energy says that energy is neither created nor destroyed, but can be transferred or changed into different forms. Here's some examples of energy changing from one form to the other. Light produces plants through a chemical change from light energy into chemical energy through photosynthesis. Electrical energy can change into thermal if you plug your stove in. Uh, if you have an electric stove, you can get thermal energy out of that. Heat up the burner. Chemical energy and the mechanical. You eat the ice cream, it gives you energy, and you are able to do things. You can eat anything and have the chemical transfer into mechanical. Uh, you can also have this in mechanized systems with chemical, like gasoline into a car will uh, help you transfer that chemical energy into mechanical energy. Uh, Mathematically, what this looks like is the conservation of energy uh, being constant. You have kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Now, we are sticking with the mechanical realm of things as it relates to gravitational potential energy and translation or motion, things that are moving. So that's kinetic energy, as we talked about before, and potential energy. I stands for initial, F stands for final. So whatever you have initially, that's what you should have in the final state of things. Uh, Another way you'll see this written is energy E initial should equal E final. Oh, what's the initial energy made up of? The kinetic energy and potential energy. What's the final made up of? The kinetic energy final, potential energy final. So they should be equal. Uh, Pretty straightforward. Now, keep in mind that this is dealing with specifically situations that there aren't any energy losses. Okay, we're going to get into that a little later, but first let's just practice, you know, balancing uh, initial and final energy. uh, and if we wanted to substitute uh, our equations for kinetic energy and potential energy, uh, the equation would look something like this. Mass times initial velocity squared divided by 2 plus mgh initial, that's initial potential energy, mgh initial, that should be equal to mass times final velocity squared over 2 plus mass times the acceleration due to gravity times the final height. So let's look at a couple of practice problems. Take some time to write down this problem. You have a roller coaster with a mass of 375 kilograms, moves from location A, 5 meters above the ground, where it has this speed, to location B, where it has this height. What's the new speed of the roller coaster at this new height? Location A is our initial location. Location B is our final location. Start off writing your conservation of energy equation. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Uh, since we have all this given information, you've got the mass of the car, so the mass is going to be the same throughout. Uh, you have the initial height, you have the final height, you have the initial velocity. Uh, so we can solve for the final velocity because that's going to be the only unknown. That's one way to solve it is to expand out these equations, solve for V. Another way people will often solve it, they'll solve for the initial kinetic energy, they'll solve specifically for the initial potential energy, and then they'll solve for the final potential energy, do the math, and figure out what their kinetic energy final is, and then use that to solve for the final velocity. We're going to do it by expanding the equation out. So our expanded equation looks like this, and now we just need to plug in numbers. We'll plug in 375 kilograms for the mass. That'll go here, 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 and here. Or you can logically see that our masses can all cancel out. So you're left with VI initial squared over 2 plus gravity times the height initial equals VF squared over 2 plus gravity times height final. Next, we're going to take our initial height, that's 5 meters, and that would get plugged in here. And our final height, 20 meters, is going to get plugged in there. Our initial speed, 20, will get plugged in here, and we'll solve for final velocity squared. Plugging in the numbers looks like this. And now it's just a matter of solving. 20 squared is 400 over 2. That's going to be 200. 9.81 times 5 is 49.1. VF squared over 2 stays. Plus 9.81 times 20 is 196. And do the math to solve for VF. 200 plus 49.1 minus, subtract over the 196, is going to get you 53.1 on this side of the equation, and VF squared over 2 comes down. Multiply both sides by 2. That equals 106 on this side. Rounded, 106 is equal to VF squared. Take the square root of both sides. Square root both sides. 10 VF equals 10.3 meters per second. And I know it's meters per second because I'm in fundamental units up here, so I'm good to go. 10.3 meters per second. That's the final velocity when this roller coaster car gets up to this 20-meter elevation. What that means is it's going uphill. And you can tell it's going uphill. Well, clearly it is because it's slowing down. Okay? It's slowing down. Okay? There's some reference energy, zero energy level here. And you have a car here at 5 meters. And it's going up to 20 meters above some arbitrary zero. Probably the ground in this case. Next problem. A person with a mass of 67 kilograms walks off a diving board 10 meters above the surface of the water. What speed will the person have when they hit the water? So the key here is to understand that they're saying that the person is walking off the diving board. They're not jumping, they're walking. So we're assuming that our initial velocity in this case is 0 because he's walking off the diving board. What makes that nice, the fact that the velocity is 0, is that our initial kinetic energy is 0, because kinetic energy is mass times velocity, mass times velocity squared over 2. Well, if velocity is 0, that whole term would be 0. So if we look at our energy equation, we can recognize that the initial kinetic energy is 0. So it just cancels out. Why is it 0? Because the initial velocity is 0. mv squared over 2, plug in 0 for velocity, you're going to get 0 for the initial kinetic energy. Now, you can pick the reference point as the surface of the water, okay? Because then your height for the initial potential energy is going to be 10. This is going to be your initial height. HI, not high. So let me do a quick drawing here. Water, diving board. We pick the water as our 0 energy line. And this diving board's at a height of 10 meters. So when this guy hits the water, guy or gal hits the water, they're going to have a final height of 0. Well, that cancels out this term because 0 times gravity times mass, or mass times gravity times 0, because we'll have a 0 height in the final spot, that's all going to be equal to 0. So you have a situation where your initial potential energy is equal to your final kinetic energy. And we're trying to figure out the speed that the person hits the water. We plug in all our numbers and solve. Mass times gravity times initial height equals mass times final velocity squared over 2. Now these masses will cancel out again. And we plug in our 9.81, our initial height of 10, solve for final velocity squared. And 9.81 times 10 is 98.1 times 2 is 196. Excuse me for the color change. 196, which equals VF, the final squared. Take the square root of both sides to get your final velocity. V final is equal to 14 meters per second, 14.0 meters per second. The last question is King to Ka with a vertical drop. I'm assuming that is some sort of roller coaster ride. Roller coasters are very popular in kinetic and potential energy problems. They've got the speed of the riders at the top of the hill, so they're giving you an initial speed of the rider at the top of the hill, the top of this vertical drop. So they're coming over the drop, and they're going to have a velocity of 6 meters per second as they're going into their vertical drop. So we can assume this is our initial velocity at the top of the hill. What's the speed at the bottom of the hill? Well, let's make the bottom of the hill the 0 energy line. So essentially, if it's at the bottom, we'll say our final height will be 0. So we write our conservation equation, and our speed at the bottom is what we're trying to find. So final velocity through finding the final kinetic energy. Height final being 0 at the bottom cancels this out, the potential energy final. And we plug our numbers in and we can solve. One thing I want to note is there may be times when you're specifically asked for the kinetic energy. Okay, you may be asked, okay, here's all this initial stuff. What's the final kinetic energy? So for cases like that, I'm going to do this problem first by solving for the final kinetic energy and then I will solve for the speed at the bottom and show you how, that minor difference in procedure makes a, makes no difference in finding the final speed. But then you'd have a little bit more information. You'd know what the kinetic energy final at a certain spot is, and sometimes that's important if you have a problem where, hey, I have the final kinetic energy at this spot, maybe I want it up here. So if this is a roller coaster, and we're specifically dealing with the situation where, this is the 127 meter drop, and this is our final kinetic energy spot. We may want to know that if uh, the event continues and we say, hey, find out what happens up here. You may want to know what that kinetic energy final is. It may be helpful in future problems. So mv initial squared over 2 plus mg initial height is equal to kinetic energy final. Again, I'm going to solve for the kinetic energy final first. Check that. This is a bad problem to do that for. Probably could have done that in previous problems. So change the kinetic energy final to showing mv final squared over 2. Reason being, they don't give me the mass up here, so we got to have those cancel out. So I won't be able to do what I had previously said, where I solved for the kinetic energy final. But hopefully you can see that it's fairly easy to achieve if you just don't cancel out the masses. But here the masses cancel out, and now we're going to continue solving the way we had done before. Plugging our numbers in, 6 gets plugged in for the initial velocity squared over 2. Add that to our gravity constant times 1.27, excuse me, our acceleration due to gravity at our gravity constant. That gives us 18. That yields 1250 equals Vf squared over 2. Going further calculations, we've got 2,536 equals Vf squared. That's from the addition of these two and multiplying by the 2. And don't forget to take the square root of both sides to find your final velocity. It's the most common error that I see. And Vf is equal to 50.4 meters per second.